Good morning, dear students. So it's been, I think, 2 months that we have not met. So we were discussing power series actually, no, unit 3. We have completed discussing uh, Taylor series, and then the lockdown happened, and so we have been discussing all the topics through Google Classroom or WhatsApp. So it is virtually. So I think we will discuss some of the portions through video class so that you could understand easily. Okay. So first, I think I will discuss Lorentz series. Okay, this is the first topic that I started through Google Classroom. Okay. So actually, what is Lorentz series? So when we are discussing power series, okay, we got to know that uh, um, when we are discussing Taylor series actually. So what is Taylor series? Taylor series, we can expand a function by Taylor's expansion, okay, or we can get a Taylor's expansion of a function if it is analytic only. Okay, so we can expand a function by Taylor's expansion if it is analytic only. But what will happen if the function is non-analytic? Okay, so that problem is solved by Lorentz expansion. Okay, so if the function is not analytic, okay, in case of non-analytic function, so again we have one expansion. That expansion is called Lorentz series. Okay, so as I have given you that what is Lorentz series. Lorentz series is of this form. Okay, Lorentz series, and you see that it is a sum of two series of the type this one. Okay, means it is earlier in case of your Taylor's expansion, the series we always got the expansion in case of positive powers. Okay, but in Lorentz series you have seen that we will get sum of two series of the type. One is positive powers of z and another one is negative powers of z, which respectively consist of the sum of positive and negative powers of z. So that is the advantage of Lorentz series or Lorentz expansion. First thing is that we can expand the function if it is non-analytic, and second thing is that we will get two type of expansion, that is positive powers of expansion and negative powers of expansion of z. So first then we will discuss Lorentz theorem. Okay, so in this case what we are considering, two concentric circles C1 and C2. Here you see this is C1 and this is C2. Two concentric circle. Concentric means their center is same. So here the center is A. Okay, having their radius R1 and R2. Okay, so let C1 and C2 be two concentric circles of radius R1 and R2 respectively, and center is at A. Okay, so here we are supposing that the function, any function f of z, is analytic on C1 and C2. That means over the region C1 and C2 the function f of z is analytic. And here we are talking about the annular region. And what is annular region? Annular region means this region. Okay, so annular region is what? Actually it is R1 minus R2. Okay, and we have assumed that the function is analytic at this annular region also, and we have given it the name R. Okay, so what will be the expansion of f of a plus h? F of a plus h will be what? A0 plus a1h a2h square plus a minus 1 by h plus a minus 2 by h square plus a minus 3 by h cube. So here in equation number 1, you see the expansion of a plus h. F of a plus h, you have seen that all are positive powers, sum of positive powers as well as negative power. So in this case from 1, so what will be n? N is, so just you remember the earlier formula. It is same. What is n? N is 1 by 2 pi I close integration over c1 f of z divided by z minus a to the power n plus 1 dz. This is all are coming from your Cauchy integral formula. Okay, so here value of n goes from 0 1 to 3, and similarly for a minus 1, that is the negative power subset. In this case also it is 1 by 2 pi I, and it is close integration over what? C2. Okay, C2 z minus a to the power n minus 1 f of z dz. Okay, and from 0 1 to 3 like this. C1 and C2 being traversed in the positive direction with respect to their interiors. The coefficient can be so, as well as in a single manner, how we can write it? A n is equal 1 by 2 pi I close integration over C. Okay, so suppose the entire circle is C now. F of z divided by z minus a to the power n plus 1 dz, and from 0 now it is plus minus 1 plus minus 2. Okay, so we can take plus minus 1 plus minus 2, that means whatever it is negative power, it will be minus 1 minus 2 like this. Whatever it is positive powers, it will be 1 2 3 like this. Okay, so earlier equation can be, the expansion can be written as f of a plus h is equal this one. Okay, a naught, then what will be the positive power? It will be a1 z minus a. This is all about your power series formula, all are coming from your power series expansion. Then see, your negative powers are coming like a minus 1 by z minus a plus a minus 2 z minus a whole square, and what will be the next? It will be a minus 3 divided by z minus a whole cube like this, where your an will be 1 by 2 pi I close integral over C f of z divided by z minus a to the power n plus n. Okay, so what will be the expansion of the whole function f of z? Now it is summation n from 0 to infinity n z minus z naught to the power n plus summation n from 1 to infinity. It is a minus n z minus z naught to the power n. So this is the expansion of f of z. Now you see that here in the expansion we are getting two kind of expansion. One is positive power sub z and another one is negative power sub z. Okay, negative power sub z means actually it is means z minus z naught to the power minus n, and n is the coefficient here, and here the coefficient is a minus 1. So in this case we will get the expansions like z here we will get the expansion like z inverse. Okay, z square z minus 2 like this. So this is actually your Lorentz expansion. So here also the positive part, okay, positive powers of z minus z naught in the expansion, it is generally called the regular part. Okay, and from 1 to infinity a minus n z minus a to the power minus n, it is called the principal part. Okay, and which is the part involving negative powers of z minus a. Okay, so remember two parts are there. One is regular part, that is positive part, and another one is principal part, that is powers involving with the negative part. Okay, so next just we will discuss one example. Suppose you are taking the function f of z is equal sine z divided by z to the power 4. So what we will do, we know expansion of sine z, so just you expand sine z. So it is 1 by z to the power 4, just expand sine z, it is z minus z cube by factorial 3. This is general power series expansion. Z to the power 5 by factorial 5 like this. So what will be the expansion here? It will be z 1 by z cube 1 by factorial 3 1 by z plus z by factorial 5 minus z cube by factorial 7 like this. Here you see in the expansion you are getting all positive powers as well as negative power subset. See, 1 by z cube 1 by z, these are negative powers of z. Why negative powers? Because it is basically your z to the power minus 3, and this is your 1 z inverse. Okay, so this is the expansion of Lorentz expansion. Here you see when we write in the manner of positive and negative powers, this is your positive powers of z, and this is negative powers of z, and here we have already discussed that this is your regular part and this is your principal part. Okay, so this is all about Lorentz expansion. This is the basic idea of Lorentz expansion. So what is Lorentz expansion? So in case of Lorentz expansion we will get two kind of things. that is positive power subset as well as negative power subset. And another one is that in case of Taylor's expansion, we can expand it only if it is analytic, but if it is not analytic, then also we can expand through Lorentz series. Okay, that's all. Okay, next video we will discuss one more topic.